Okay. I'd like to start off by saying good afternoon to everybody and thank you for joining us today for our AIA presentation on converting office space to labs. As we've all seen, the life science market is booming and the recent pandemic has prompted it to flourish in unprecedented ways. Converting an existing office building for lab use requires a highly technical analysis and as well as a complete understanding of the building systems. For example, the building infrastructure necessary for laboratories is much different from the standard design parameters for a typical office building. Our DC office has worked with Digene headquarters, now QIAGEN up in Gaithersburg, Johns Hopkins Applied Physics Lab, MedImmune, FDA, and other private and government entities in the design of their facilities. At this time, I'd like to introduce Bala's team of laboratory experts. We have Chuck Kensky, who's the Executive Vice President, Director of Engineering. Chuck has over 30 years of experience in managing the engineering for laboratory and mission critical spaces. We have Scott Davis. He is the Vice President, Director of Mechanical Engineering, and Scott also has over 30 years of experience focusing on complex laboratory and mission critical projects. He's often called upon for his technical knowledge and expertise. We have Stephen Anastasio, Director of Structures. Stephen has over 15 years of experience in design, including many adaptive reuse and building renovation projects suitable for office to lab conversions. As we welcome our team of experts, I'll let them take it from here. Thank you.
Thank you, Donna. Next slide, please. So we're going to go through the AIA course requirements so that everybody gets their credits. Basically, they're going through the course description here. You all have your numbers turned in. We'll go through some learning objectives. We're going to talk about the infrastructure considerations when we convert an office to a lab, some about the marketplace and the future of planning for life sciences, the infrastructure requirements, how they differ from a common office to a lab space, and Steve will get into a lot of the structural implications. Okay, next slide. So we'll take you through building evaluation. Scott's going to run you through all the metrics, and we'll go through planning, case studies, and lessons learned. Okay, so we want to talk about the building evaluation. So the concept here is we've got a lot of phone calls from developers and building owners that say, can I convert my building over to a lab? What's going to be involved? Is it feasible? So we go through a number of metrics and we go through another of evaluations to determine what we can do. So we talk about location. Is it urban, suburban? Do we have parking? Is there access to the building for deliveries? Is it in a neighborhood or is it in a city? We look at high rise, low rise. High rises have a different challenge because we have a lot of shafts we have to put in the building for the exhaust air and equipment that's going to be on the roof, makeup air. So it makes it a little more difficult by putting in the shaft space. Also, in a high rise, you have different limitations relative to the amount of chemicals that you can store, flammable liquids you can store higher up in the building. So you'll see that sometimes they'll build a chemical storage facility lower or a room lower in the building and transport up daily use amounts higher up into the building if you're working in a high rise. Other concepts and discussions are property adjacencies. Am I directly next to adjacent buildings? In other words, are they touching my sides and I only have access to the front and back? Or are they higher or lower than my building? Will anything that I'm blowing out of the building, my exhaust, will it affect my neighbors? So how close are they? Also take into account zoning restrictions relative to ordinance, setbacks, noise, exhaust restrictions, the construction type. Was it a flex office? Was it a dense pack? Is it a data center now? It's going to be something later. These all come into play when we start evaluating the building and what we can do with the building.
So they did bring me in as a
I'm sorry? Okay, so then we move into the due diligence portion of the study where we start looking at utilities. So for mechanical, is the building chilled water, condenser water? What are the capacities? Can we expand them? Do we need to keep them separate from the base building if we're doing a portion of the building? Ventilation and exhaust system, what's there? How do we add more? There's going to be a lot more added because of all the exhaust for hoods. Do we have steam in the building? Or are there boilers in the building? Do we have steam available from the city that we can put into the building? These are usually required for specialty equipment like autoclaves or humidification systems. We talk about power. Look at our power. What's available in the building? Do we have enough power? And you'll see in our metrics that Scott will run you through how much power we're going to need. Do we have enough in the building, or can we add it to the building? Can we bring in another service? Does it have an emergency generator? So typically you'll see most buildings have a small life safety generator. That's not what we're talking about. We're talking about emergency backup to run equipment. And we're going to be running lab equipment so that the scientists don't lose their experiments. Anything in the Petri dish in a refrigerator would die if it didn't have its cooling. Like with the vaccine, it's got to be kept cold. But also our fans and our equipment have to continue to run. So we evaluate the base. Our evaluation is based on what type of office and what type of lab we're going to do, and the mix between office and lab. And that's how we evaluate the power, what's available. We look at our water, what's available with the water, because you're going to be using more water with a lab. And we get into our sewer because you're going to see acid neutralization coming out of the labs. And how do we handle that? Do we need to increase the water resource service? And one is always a key is natural gas, because a lot of times it's used within the labs as our specialty gases, but also for potential mechanical equipment for heating and so forth. So wind wake and acoustics, these are two things that we always recommend. And this is where we bring in a specialist onto the project, or we require one on the project to go through and evaluate a complete study of the exhaust. So I call them the gazintas and the gazatos, what we're exhausting out of the building, what we're bringing in for makeup air. So for example, we want to make sure that what we're exhausting, any kind of fumes, chemicals, is not being entrained into our own intakes, but also our neighbors' intakes. So a lot of times a wind wake analysis will be a computational fluid dynamics study where they evaluate the building based on prevailing winds, and they determine with the velocity of the exhaust how the plume is going to go, okay? We've actually had buildings where they build a life scale model, they studied the wind patterns, and then they put it into a wind tunnel. So there's multiple ways to do that. Acoustics are critical because vibrations can be an issue. It can be an issue because of the type of lab, the sensitive equipment, or the animals that are in the lab, but also with your neighbors. Their building may not be 100% lab. So you could have office neighbors within the building and anything outside the building with acoustics, generators, chillers, major air hands, or exhausts. They could affect buildings adjacent to you. So those are parts of the study that we always go through to see what we need to do to mitigate those types of outside noise. We look at the equipment space and pathways within the building, because there's going to be a lot of equipment being added. Some of it will be on the roof, some of it could be on the floor. When I talk equipment, I'm talking MEP, but there's lab equipment as well. So you have back of the house areas like autoclaves, refrigerators and freezers, storage areas. These things they take up room. You're going to need pathways to bring chemicals, bottled gases, supplies, filters in and out of the labs. So adequate space to be able to bring in supplies up and down and throughout the building. Structural framing, what is the loading of the building? What's the floor loading? We're going to be adding a lot of equipment. We're adding a lot of ductwork. We're hanging a lot of pipework and conduit from the floor above. So not only are we setting stuff on the floor, casework, fume hoods, equipment, we're hanging from the floor below. So we need to go through the analysis of what is the structural framing. Steve will dig into that more in depth here. And what types of slabs do we have? Do we have clear spans? Do we have waffle? If you look at the upper right-hand picture here, that is a clear span. That is a two-way flat slab. So there's no beam sticking down, bar joist, no waffle or anything. It's just clear, flat to flat. All right, and that's a good one to run all our ductwork and our equipment. When I mentioned there's a lot of power being added to the building, if you look down the next two slides, the middle one is the new electrical gear that usually gets put into the building. And you got to find not only a home for that, but it's got to be able to be supported by the floor weight, the floor structure. And then the bottom picture, you see generators outside on grade, and that's great. If they can't, they can be on the roof in a high rise, but we need to find a home for them because we will need generators. Last thing we kind of look at in our due diligence is our deliveries. You're going to have a lot of material, as I mentioned, coming in and out, glassware, filters, paperware, bottled gases. So you're going to need freights, you're going to need docks and bringing in the equipment. But if you're also considering a vivarium, you want to be able to keep animal transport separate from human transport. So those are the things we do when we go through a building evaluation and do the due diligence and then complete the study and move forward from there. Okay, next slide.
So in terms of the structure, the bones of the building, if we're starting off with office space, then the building is likely a steel frame building, especially if it was built within the last 30 years. However, occasionally we can find ourselves in these different construction types, which can have different issues when we're converting them over to a lab space. In terms of what's important when converting to lab space, the two biggest scope items that affect the structure are one, the building's ability to support the weight of the infrastructure, as well as opening up the floors and walls, which can include a significant amount of chopping for the lab conversion. Also the vibration performance of the floors varies between these construction types. This is important because a developer may want to sell their space to qualify as having a certain level of vibration performance and stiff enough floors to not disrupt the tenant's lab activities and equipment. So without going into detail, this table is set up to describe how well these systems work for each type of building system. With A being the best and requiring likely the least amount of cost to upgrade, and F being the worst and requiring significant amount of retrofit and reinforcing to bring it up to par. Generally, conventional steel usually proves to be the best. This is what we would design a new spec lab building today. Well, when we go back into the 70s and 80s, it's not uncommon to see open web joist frame systems, which has their own issues with generally being designed cheaply, and the floors don't have much mass to absorb the vibrations. Also, their joists are spaced pretty close together, making it difficult to cut chases in the floors. And then when you go back before the 50s, there still is a good crop of robust buildings out there. However, they require their own attention to bring up to par.
Okay, I'll take us through the metrics next. So in the next two slides, we're going to evaluate what you might find in a typical lab compared to an office. And then on the next slide, we're going to look at specialty labs, clean room type labs, and vivarium. So staying with this first in the pass here at typical labs, you can see our first dramatic increase is going to be with our need for outside air and exhaust. We're going to be generally seeing values between 1 to 2 CFM per square foot. And that's going to be predicated on the types of labs that we're dealing with, whether they're biological or chemical in nature. Chemistry type labs just tend to have more fume hoods in them, more dense layout. So they're going to be closer to the 2 CFM range. And a biological based laboratory, which may rely on a combination of fume hoods or zero fume hoods and biological safety cabinets, they'll be on the lower end at that 1 to 1.25 CFM. And one thing we have noticed, there are some geographical differences. We noticed between our offices from DC up to Boston. And we're finding the Boston market is gravitating more toward the 2 CFM per square foot, but that could also be due to just the type of laboratory space they're looking at, which is chemistry, as I mentioned. Or we're also seeing factors that are driving this as far as a speculative type nature of the business, where the developers are looking to maximize the space that they can rent out, and so they're leaning more towards a more flexible design, which gets them on the higher end of that range. Next, we could look at normal power. We see there's about a 3-fold increase as you go from office to lab, and this is the 15 watts per square foot is dedicated to lab bench type work. The HVAC equipment increase in power is above and beyond this 15 watts. We might see even as high as like 20 to 25 if you combine everything together. We also see with the introduction of lab space, we need standby power. So in your typical office arrangement, you may just have a small life safety generator, or things are on battery, like such as light fixtures may be on battery power. But with labs, there's definitely a need for standby power, and this means at least a small generator will need to be utilized for this purpose. And this is to satisfy the lab tenant requirements for their critical equipment. And essentially, we're looking at refrigerator freezers that may be storing, say, tissue samples, It could also be utilized to power any sensitive equipment, maybe equipment that once running would be detrimental if it was disrupted. Because what we see here are the scientists have an investment made in the work that they're doing, whether it's that tissue sample I mentioned, or if it is maybe a particular process. But that tissue sample may represent 6 months worth of work, so they would not want it to be destroyed. Say had the power going out and the freezer was stored in warmed up. So this need for standby power is really to protect their assets and to keep their work going. From the fire protection standpoint, there is a slight uptick in hazard classification, but from a hydraulic standpoint, it's essentially the same. It may require maybe a couple additional heads in certain rooms, but for the most part, it's really almost a one-for-one comparison. So which is nice, so that as we see with fire protection systems, we don't see a huge change in what's required. Next, we look at supplemental shaft space. So for a typical conversion that we're talking about here with the 1 to 2 CFM per square foot, we're seeing roughly a 6 to 8 square feet of extra area required on a floor to accommodate the outside air, the new outside air and exhaust. And to put that in perspective too, this is roughly for a building footprint of about 20,000 square feet. So if you have, say, a larger square footage, up to 40,000, then you would see basically twice this amount. So then you need 12 to 16 square feet of shaft space. But again, just to give you a rough idea of the amount of area you would need to allocate when considering conversion. All right, next, floor to floor heights. These can be challenging, as a typical office is going to be about 12 and a half feet. With a laboratory, we prefer 14 and a half feet. That will allow everything to fit comfortably, but does not mean we can't work with 12 and a half feet. It's still possible, and there are different techniques that we would apply here. And one of them might be to develop what I'll call horizontal mechanical MEP type spaces that run along the length of the labs. And essentially what that allows us to do is to feed from the side our utilities as opposed to overhead. Obviously, with a situation like that, the downside is that you're going to lose rentable space or laboratory space if, as far as what you can work with in your footprint. So there is a challenge with that. So that has to be obviously fully vetted with your clients, your landlords, when considering such a process. Next, we'd like to look at some specific structural criteria. Steve, see if you could jump in here.
Yeah, so per code, the floor load capacity per code would be 60 pounds per square foot. However, when we're looking at these office buildings that are already built, we notice about half of them already satisfy 100 pounds a square foot. Either they were originally designed and had the foresight to use 100 pounds a square foot, which is good because if we were going to do a new lab building today, we would do 100 or 125, which would help support any local equipment and heavy lab activities on the floor plate. The other half of them, however, were code minimum for an office, which is 50 pounds a square foot. And then if we encounter those, it's not too hard to upgrade them. It'll still require some local reinforcement on the floor plate at the heavy equipment. However, there's always residual capacity in the floor frame, and as well as there's usually a partition allowance of 15 pounds a square foot that we can borrow from. And then for the vibration requirements, this gives you an idea of the difference between an office requirement and the bare minimum lab qualification. It's almost off by a factor of 8. So typically it's pretty expensive to upgrade the entire floor of the lab to qualify for this requirement. So what we've seen is depending on the piece of equipment or the certain lab activities that are more localized within the building, we'll just reinforce those specific areas.
Hey, thanks, Steve. One other quick note for that one too, with the vibration. There are sometimes scenarios where the lab users themselves can help mitigate vibration. And that's in the sense that if they have a particular sensitive piece of equipment that's mounted on a bench, they're able to utilize what's called an air table, which is essentially an air hockey table. But the sensitive equipment rests on top of this table, which then suspends it on a bed of air. And essentially that eliminates all vibrations that may come in through the floor vibrations. And essentially that allows us to avoid some of the modifications that Stephen just mentioned. So again, the cautionary note here is just we'll talk it through with the potential clients, potential lab users. There may be relatively inexpensive solutions to their needs. Okay, next slide. Okay, as I mentioned, we're going to take a look at clean space, clean laboratories, and vivariums on this slide. So you can see actually with both clean and vivarium, the outside air exhaust requirements are pretty close to what you see in a typical lab. On the clean space, it's essentially the same. The amount of outside air is going to vary based on the type of work being done, as far as if you have a high fume hood density or a low fume hood density. With the vivarium, it's a little bit different in that the variations you see here are based on the animals that will be housed. So your larger animals, canine and swine, will be on the larger end of 2.5 CFM. Your smaller or rodent animals will be on the lower end, the 1 to 1.25 CFM. And even further reductions can be had with vivarium if you utilize a ventilator rack system to house the rodents. And essentially what that allows us to do is to provide the desired air change rate ventilation, but it's predicated or based upon just the internal volume of the individual racks as opposed to the entire room volume. So essentially a typical room might need about 15 air changes of airflow. If you utilize ventilator racks, you could drop that down to about 6. So you can see it's almost a threefold decrease. So it does pay to have that discussion with your client, your typical lab user, to understand what their real needs are, because that can help formulate how you put these designs together. And then one important note is that the more we can reduce the amount of outside air, exhaust air required, the easier the conversion can be. So again, on the one hand, you want to right size it to what your clients need, but at the same time, you don't want to shortchange it. So it's always a delicate balance, and it's definitely something to be reviewed during the programming phase of the project. Okay, next, looking at normal power and clean spaces. It's pretty much even with a typical lab. Standby power, we do see an uptick with clean spaces. And this is due to the critical nature of the work. These tend, in clean rooms, they tend to be more critical as opposed to your typical lab. So we're seeing it almost even with your full load. So it's important to note that there would be an increase there. Fire protection is pretty standard, again, as a typical lab, so it stays the same. Supplemental shaft space, again, since our exhaust and outside air is similar to a typical lab, we're going to have the same kind of numbers as far as 6 to 8 square feet per floor. The floor-to-floor height, though, you can see jumps up. Again, this is the 16-foot represents a preferred method or preferred dimension. Of course, we can, again, work with lower dimensions, but ideally it would be the 16-foot. And this is really predicated on the fact that with a clean room space, as I mentioned, we have the 1 to 2 CFM per square foot of outside air, but clean rooms need to maintain about 20 air changes to maintain their classification. And that's 20 air changes of recirculating air. So we're roughly running 3 CFM per square foot total, and we blend in the outside air. But that 3 CFM per square foot represents a large volume of space needed to accommodate that ductwork. So ideally with a clean space, you're locating your main primary moving equipment, air moving equipment, next to or adjacent to your clean room spaces. That way you're not dragging your ductwork up and down floors, because that would require additional shaft space. Now, having said that, then that's why we need the 16-foot. Now, so in the situation where we're dealing, say, with that 12.5 foot office floor to floor space, again, there are a couple of options we can look at. We can look at the horizontal mechanical MEP type chase spaces next to these clean room suites. Another option is actually to utilize a floor space above as a mezzanine. and feed down into the clean room space. So on the one hand, it's detrimental because it's going to chew up a lot of rentable floor space or available space. But on the flip side, again, it does allow you to put a clean room into an office type environment. And we have a couple of photos we'll show later on that kind of demonstrate some of these projects we worked on that can highlight that. And moving over to Vivarium again, with the normal power, we see a range. I'm showing a range here about 15 to 30 watts per square foot. So typically the Vivariums are going to be very similar to Labs. The reason we're showing the 30 watt per square foot is with Vivarium, you need clean cage equipment, and they utilize steam. So if you don't have steam available or natural gas, then you're going to need to generate your steam with power. So in those scenarios, you're going to find yourself close to that 30 watt per square foot range. So it's really going to be predicated on the type of equipment you have in your cage wash area, whether you have the 15 or the much higher value at 30. Standby power is similar to clean space in that the power is more critical in this situation for a different reason, but more critical than your typical lab. Here, the standby power is really needed to keep the animals comfortable. There are certain governing agencies, ALAC and NIH most predominantly cover this, but they go to the well-being and how the animals need to be taken care of. But beyond that too, there's a vested interest by the scientists to keep the animals comfortable, because after all, they're part of the science that they're conducting at the moment. And there are stressors that will impact the research that's being done. So it's very important to keep the animals stress-free. And one way to stress them would be to lose air conditioning. So it's important in Vivarium to make sure you have that level of standby power. Similar to a typical lab, the fire protection, the shaft space, even the floor-to-floor height's pretty similar. And again, we can work with less than 14.5 feet, but again, that's the ideal. And then, as Steve mentioned on the previous slide, the structure was pretty similar for these spaces. The only thing I want to mention was the vibration. The vibration is another stressor for animals. They will be very sensitive to that, and they can pick that up, even if it's at a level that we can't feel or sense. So it's important to make sure where the animals are housed is definitely vibration, very low vibration type free. So again, as Steve mentioned, there are techniques though that you could apply where you're just stiffen the steel, say in the area where the animals are housed. So again, it's not for the entire area of the vivarium, it would really just be where the animals are housed. Okay, next slide.
Steve, Scott, we have a question on the height of the
Sure.
clean room. What would be the clear height of the inside of the clean room if you had a 16-foot floor to floor?
Typical would be about 9 foot at that level. And it's an excellent point. In all these values we're given are based on a 9-foot ceiling for both Vivarium, clean space, and lab. So obviously, if you're able to drop your ceiling heights, so that's another way to work that in, because we actually have done that on a couple projects where we might be looking at 8-foot ceilings in order to get some of these to work, where we have less than the 14.5.
So the one key thing here is the air changes. As you make the room volume larger, you have to move more airflow. So it makes the air changes per hour even higher. We have another one here on the bar joists. Does the 14.6 inch recommended account for the bar joists?
So the 14.5 feet would be total floor to floor, whether the structure is concrete, it could be bar joists as you're mentioning here in this question, and regular steel. I mean, I would say one thing with the bar joist, bar joist gives us a little more ample room to thread our utilities through it. So in some respects, sometimes the bar joist systems are preferable when we have low floor to floors.
We have recently looked at a bar joist floor building, and the bar joists were on 2-foot centers. So that means we can't put any of the equipment up there, like VAV boxes or exhaust valves or anything, because there's no clearance to get it in there, service it, maintain the clearances. So while on one hand, bar joists may work to put piping and utilities through it, it limits us for access for other mechanical equipment that we would put up there. All right, next slide.
Okay, just to jump into here, as Chuck mentioned earlier, once we evaluate the building, we look at some of the unique things regarding planning that we look for. So just to start this off, as I just mentioned in the metrics, the type of lab really comes into play. So it's important to understand the type of lab that you're targeting to build. You know, in the case too is if it needs to be flexible or not. So like in the case of an incubator hoteling type setup where you have a landlord who's going to be renting out space and maybe be renting out linear feet of bench for different clientele. It's important to know that because with an incubator type setup, you probably need a lot of flexibility. And you got to be under, it has to be designed such that the space is being shared with a bunch of different tenants. If you're looking at even speculative type lab layout, that's another area where it kind of dictates you might want to go for a more flexible approach. And as I mentioned, we're seeing that in the Boston market a lot. If you have an anchor type tenant, or if the tenant's taken over the entire building, that will obviously make it a little bit easier to hone in the design. You can be maybe less flexible. And then you can deal directly with them to provide their specific needs. But again, even if you do have an anchor tenant, doesn't mean that tenant's going to be there in 5 years, say, or again, it really depends on the lease arrangement. But because you have an anchor tenant, I would just caution, doesn't mean you don't necessarily have to give up on your flexibility. You can still do flexible design, and it may be advantageous for the landlord at that point to stay with that kind of approach. As I mentioned, if you're dealing with specialty type spaces like Vivarium and clean rooms, that will steer you in a different direction. You're going to need more power, more HVAC. So it's important to understand if you have these spaces, and if you do, how much square footage wise, because it will come into play. Chemical use and storage is also a key especially when we're looking at the high-rise type situations in urban environments. Code will dictate the amount of chemical allowed stored on different floors. And as you work your way up the building, it starts to cut it off. Actually, at the 4th floor, there's a severe reduction that's allowed. And the reason I'm bringing this up is because, again, as part of planning, you need to understand the storage needs of your clientele. And if you're dealing with a situation where you do need to develop a higher floor levels, you can still put in a chemical room, storage room at your base of the building. And essentially think of it like a rentable locker type space where it's just a large area. It could be segregated by fencing to secure it, and essentially each tenant could have their own space. And what this will allow them to do is to store the chemicals they need to do their normal operations. And then it affords them the ability to move them from the ground level up to their floor on an as-needed basis. That way, when they're shortchanged on what they can store on the floor level by code on their particular floor, they can still store it in the building at the lower level where there's a lot more volume allowed to be stored. So it goes into just developing that communal area and making sure it's secured for each tenant and easily accessible. Okay, Chuck, you want to take it from there?
Sure. So we talk about the how much infrastructure do we need to provide? So this is working with your client, working with the developer, and how is his deal structured? So we have projects where we're just providing the utilities to the spaces. In other words, water, air, power, exhaust, stuff like that. And then the tenants coming in, a part of their fit out, they're providing the air handlers, the autoclaves, all of the equipment, the generators to fit out their space. Okay, so you have to understand, where do we draw the line? If it's going to be a full turnkey, then we're providing everything. We're designing all the utilities, all the equipment, ceiling tiles, lights, everything. So we need to understand what that is. Where is the equipment space going to be? We have to do an idea of, I need to add air handlers, exhaust fans, potentially generators. Where are they going to sit? Are they on grade? Are they on the roof? We have to do that analysis. We have to work it out with the client on where the infrastructure is going to sit. Shaft space, as Scott said, so many buildings are long and slender with an elevator core and toilet core in the middle. So that kind of lends itself to being 2 shafts for that building, even though it's only 25,000 square feet or so for floor plate, because the elevator core blocks access to the other side. And it's a long, skinny building. So going through how we're going to do our shafts, how many floors are going to be involved in the renovation, what are our louver and our roof space? So we've got, like I said, the air coming in, the air going out. Louvers typically can go on the outside if it's not a historical building. Otherwise, we have to go up to the roof. We're typically not exhausting out the sides of buildings due to property lines and limitations that way as far as our exhaust and our plumes. So we have the additional makeup air we talked about, standby power. You get into specialty systems. So to the developer, to the client, is this just utilities? Will the tenant provide their own vacuum exhaust system, their own vacuum systems? Do we want to do a central one? So it's a spec lab. We're going to have multiple labs and then tenants can tie in as they come. Same thing with compressed air, purified water. Those are the systems that it needs to identify. Do we need to put it into the base building? Will it come with the tenant? Or are we doing, like Scott said, we're doing an anchor tenant that's going to need all of it day one. And then the acid neutralization. A lot of these things require extra service, extra maintenance that a normal building operator is not familiar with if they don't run labs. So sometimes the acid neutralization, the developer will say it's going to go on the tenant, but the tenant's like a small startup. It's a scientist starting his own thing. He's doing a flex lab. He's not going to be running and maintaining this equipment. So that's how you have to work it out, develop the scope with the client and go through the planning process to determine what is going to be in the project and what's going to be in the tenant project, or if you're doing both together as an anchor, what's involved in the project. Next slide. So when we get into the actual planning and looking at the building space, they always want to know cost. So we're always working with the developer, working with construction managers and contractors to come up with an idea of what is the order of magnitude costs. These are not detailed construction estimates. What other usages, other spaces, what control areas we're going to need in the project. So if you can look at the lower left picture, that is a rooftop of a building up in Boston, 451 D Street. That is a long, skinny building. It's a whole city block. So part of our study is going to be, what spaces on the roof do I have to add the additional equipment? You can see there's 2 alleys and then 2 streets. So I don't have a lot of room to put a lot of stuff on grade. I'm right up to the sidewalk. So you go through and you look at what's existing, what do we have to add, where the labs are going to be, and you do the analysis based on what part of the analysis of what's my ability to put equipment on the roof. Now, costs, we talk about costs. We do the study based on breakpoints. So the client says, look, I have 500,000 square feet. How much lab can I put in it? We talk about the metrics of office to lab ratio, 50%, 50%. We do the cost analysis based on power. What can you physically do? And your first metric is, okay, I have so many watts available, so much kW available. I run out of power at this many square feet of lab. Or I need to add cooling towers, exhausts. I run out of space on the roof to serve this many square feet of lab. So you kind of develop a matrix that has what your breakpoints are. So if I can support more mechanically than I can electrically, I bring in a service and I make them match up. And that's the amount of space that we can convert to a lab. That's part of the analysis and planning that we do up front. And then the client says, okay, of my 500,000, we can only do 150 as lab and another 150 as support offices. Okay, now I know. And then he knows what he's marketing. Okay, next slide. So this is 451 D Street, a completed project from our Boston office. The slide prior was the roof of this building. So this is a 477 square foot building, rentable square feet, 9 stories with a basement. It's an entire city block. Okay, this building is actually 2 buildings that were abutted and joined together. One has a terracotta, 11'6" floor to floor construction, and the other one's cast in place concrete at 12'7" floor to floor. So they're very tight. It used to be an old telco service provider, so it has plenty of power, and it actually had high pressure natural gas, which is unusual for a telco. But it has 13.8 kV electrical service, 3 4,000 amp, 40 volt double-ended substations. It has 40 watts a square foot. So if you remember from the matrix, this meets the metrics. The power meets the metrics. This one's an easy home run. It's just going to be tight floor to floor. What we did to this is we added 2 300-ton gas-fired DX rooftop units that were custom units for makeup air. And then we provided a Strobic fan array, which we'll show you a picture of for our exhaust. Did a glycol heat recovery system between the supply and the exhaust air for energy recovery. And we also utilized 2 abandoned elevators for shafts for not only power and communication, but our exhaust and our water risers, so forth and so on. So if you look at the images here, you'll see that the electrical gear is there on the left. The other picture on the bottom is the actual elevator shaft that got converted to a vertical utility shaft. Next slide. So here on the roof, you'll see this 3 Strobic fans. I call them my stormtroopers. They're combined into a combined plenum. One is redundant. These things are designed to suck air in from the ambient and increase the total volume to increase my discharge velocity. We want a minimum 3,000 feet per minute out of that cone, and that can be noisy. So you can put attenuations on the cone if you need to, but back to the requirement for an acoustical consultant. But that's the Strobic fan array. Bottom left picture shows you the custom air handlers. Because our floor-to-floor height is tight and not all of the building was converted. You can see here 150,000 square feet was converted to lab, and it was spread out through the 9 floors, not centralized on the top floor or the second floor, whatever. It's spread out. So we had to run our ductwork across the roof and then down those shafts that I showed you in the previous slide. Some areas where it was tight and you couldn't get into get the service the area from the shafts, we ran the building down, the ductwork down the side of the building. So the picture on the right, you can see the red ductwork. That's the ductwork coming down the side of the building and going into the building to serve pockets of labs. That's on the alley side, so it's not the front of the building. And they painted it to match the brick, so it looks pretty good. But you can see here it was an office to lab ratio of 50-50. We provided 1.5 CFM per square foot for our makeup air and our lab exhaust. And you can see the normal power requirements were met as well as our standby power. And now this one we put in 2 pH neutralization rooms because the building was so long. And because the ceiling floor-to-floor heights were shallow, by the time you run that pipe and you slope it across the whole building, you're going below your ceilings. So it was more effective to run 2 vertical acid neutralization risers that they could tie into closer and then go into 2 separate rooms. Okay, next slide.
Okay, I'll take us through this case study. This is a particular building we're working on in the Philadelphia region. We're just finished up the designs. We're starting to move into construction now. We're lucky enough to be involved with both the core shell side as well as some of the tenant fit out, similar to the last example we just went through. This particular building, we start off with a building evaluation, similar to what we've talked about earlier in this presentation. So we looked at this building was a 29-story, a little more than 700,000 square feet. And we're looking to develop a portion of it into lab space. As our initial assessment, we did notice that we had sufficient power, thankfully. The office building itself turned out to have been designed with a little more power than what you would normally find in a office building. And we also had the advantage of a couple floors were data center. So in the end, we found that we had enough normal power coming into the building. Standby power, though, we did have to end up bringing in, providing our own generator to bolster that need. We did have access to a high pressure gas service, but in the end, we turned out that we didn't go that route. And we stayed with the electricity. And again, that's more from the fact that we had an abundant supply. Here we're looking at a floor-to-floor of roughly 13 feet, and we did happen to deal with, had to deal with a couple of deep girders in some areas. And the way we handled that was looking at our room layouts and working with the architect to move equipment around, such as a fume hood, to avoid these deep girders. Because a typical fume hood, you want a nice long sweeping elbow into it, and that helps promote good airflow into the face of the fume hood in the room. So it's important just to take heed of where that equipment needs to be and the type of duct configuration it would require. Okay, next slide.
Before I advance, Scott, we just got
Sure.
a question in asking what is the difference between converting an existing office building to medical office building versus converting an existing office building to lab space?
So I understand, right? It's convert an office to medical
Yes.
office use,
Yep.
and or versus a lab. One thing I'll say with the medical office, there are code restrictions as far that would come into play that would dictate air changes and some other facets, because basically you have to follow healthcare, and what I'm thinking of is an office. It could be a dental office. It could be a medical office where there's patient care taking place. I'm not saying it's a full-blown surgery suite. I'm just saying that, but there are exam rooms and whatnot. So we would need to follow those. But I can say from that perspective, lab would tend to be a little more needful of airflow and utilities than a typical, say, your typical medical type office building. So I would suggest that you're going to have, it'll be a little bit easier to convert an office into a medical office type building than it would be a full-blown lab. You know, you could also think of your medical office as going to be closer to that lower range we were showing earlier in the metrics about that 1 CFM per square foot. If that helps, it might even be a little bit less as far as total required, but it'd definitely be less utility intensive than your typical lab fit out. Okay, so with this building, we ended up converting, targeting 120,000 square feet. And we kind of worked our way back into that from our evaluation phase. Essentially, when we were evaluating the building, as Chuck mentioned earlier, we're looking for our lowest common denominator in the different utilities. And you know, as I mentioned, the electricity was fine. We found the plumbing was fine. Our short straw turned out to be basically the physical space on the roof where we could fit the exhaust. So essentially, maximize a space that would accommodate 80,000 CFM of exhaust. And then from there, we work backwards into, okay, if we do 1 CFM per square foot for our typical average use, that would get us 80,000 square feet of lab space. And then if we mix it up between office and lab, we could get up to 120,000 square feet. So essentially, that's what we're looking at. We're dealing with a mixture of office and lab with a maximum of 120,000 square feet. And essentially, that's being spread out over 8 floors. And as I mentioned earlier about the chemical usage, the owner in this case considered that when they were picking the floors they were going to convert. So we end up going with lower floors. But essentially, we're going to span that gap I was talking about at the 4th floor where the code kicks in and really restricts your stored volume. So in this case, we're looking at floors 2 through 9. So we'll have a little bit easier going on the lower floors, but the upper floors, they'll have limitations. And because of that, we are going to do a large chemical storage room on the ground floor so that the tenants on the upper floors still have ready access to their needs for the different chemicals they're going to need, especially the flammable ones. And as I mentioned, we're working on the core shell side, and we're also at the same time fitting out 2 floors, and we're doing them as an incubator type lab setup. And what we found as we were developing the fit outside of it, you know, our initial first pass from the potential tenants' needs, we saw that we're going to consume half of our utilities, airflow, power, just with 2 floors. So it was nice that we were able to work with them on the core shell side, are able to highlight that fact, and then work with the lab users to really think about how they want to use their space. So through programming, we're able to then reevaluate. And in this case, we basically were able to reduce the amount of fumants they're initially looking for so that we could keep the first 2 floors back to a prorated amount of the total volume of the 80,000 CFM I mentioned earlier on the exhaust. But we were able to utilize that as a tool to keep right sizing the floors, and that will continue as we go up the building. And as far as comparing to the metrics, as I mentioned, we went with the 1 CFM per square foot average. Our normal power actually was at 20 watts. So again, the numbers I mentioned earlier were averages. So you can see here we're slightly above the average of 15 watts per square foot. Standby power, we're right on that 5 watt per square foot metric. And here we ended up with a centralized lab waste neutralization system. And that was mainly because that first tenant we're dealing with is an incubator. We actually started this project off with the lab waste is going to be by the tenant. And that was mainly because the developer is fairly new to the lab game, and they didn't want to take on the responsibility of managing this system because they're just unfamiliar with it. But once they started reaching out in the market and seeing what kind of tenants they were going to be attracting and what their needs were going to be, they did get a repeated request for lab waste neutralization, especially with the incubator type spaces, because these companies can't, they're generally startups and they can't afford the infrastructure. So essentially we were able to switch that midway through the design to a centralized system. So again, here it just goes to show, sometimes the market's going to demand a certain aspect, and the developers have to be able to respond to that. Okay, next slide.
Scott, we had a question
Oh,
on
sorry.
how often do we see that the envelope needs to be upgraded for infiltration and energy codes? And I know that a lot of times it's triggered by the existing building code and the square footage or the percentage of the building being upgraded. So if you're only doing a small portion of it, you may not trigger that. We've had one project where a tenant is only taken, say, 40,000 square feet of a 1.3 million square foot building, but they wanted the landlord to replace all the windows. So the landlord's doing that, but they don't have to do that because of a code requirement or code trigger.
Yeah, and then just add to that, I would agree with you, Chuck. And then actually in this particular case, we're not touching the envelope. It's a current wall system. It's fairly tight to begin with, and we are slightly over pressurizing the space to the outside anyway. So that would also cut down on the infiltration. But it's an excellent point. It's definitely something you need to look at, because laboratory spaces are going to be more sensitive to humidity than maybe your typical office space. So it is important to look at that, especially maybe if you're dealing with an older building.
Well, to that point, we'll be adding humidification to a lot of labs, at least for the outside air, so that the
Yep.
Condensation reduction factor of the windows and the window construction and the walls does have to be taken into consideration for any condensation forming from the humidity.
Yeah, good point.
Next slide.
Okay.
So another case study, again, out of our Massachusetts office, not like the rest of us don't do work, but they just happen to have two showcase ones we wanted to show here. This is a 6-story building that is roughly 233,000 square feet. And this was actually fully designed. And it was designed as an office. And they decided, well, I'm going to switch this with everything going on. The office market was dropping. We converted it to a lab building. Didn't make it any bigger. We just converted it over with the mechanical systems, electrical systems. It went 50% lab, 50% office. You can see here of the metrics, we got 7 watts for normal power and 15 in the labs. We have 2 neutralization rooms, similar to the last example that we gave you, where it's a long, skinny building, and it made sense to do it that way. We added 2 custom evaporative cooling rooftop units to take care of our outside air quantities and serve the labs for our makeup air. If you go to the next slide. And then here on the roof, you're going to see more stormtroopers. That's our exhaust system. Down in the bottom left, when Scott was talking about the low floor to floor height issues, and there's a way to do it with side mechanical spaces, this is what he's talking about. So on a building that is a low floor to floor, you can have the labs to the left of that piping rack where they currently are, where they're designed. And then all the piping utilities are racked along the wall. All of the exhaust and supply VAVs are on the right-hand side. You can see those boxes, and they are in a service corridor that goes up and over into the labs to serve the lab space. So this is a service corridor to service the lab, service the piping, and all these VAV boxes and mechanical equipment. So you're losing on a low floor to floor, right? You're losing more rentable square footage. And so the landlord needs to know that up front, or the developer, so that he knows how does he structure his deal. If I want to repurpose this building, I'm going to lose some floor to floor because it's so low. The right-hand side, you're going to see a mezzanine. This is where you had a clean room below, and we actually cut a hole in the floor, as you saw earlier on one of Steve's slides. So there's a hole in the floor, and the clean room is below it. The mechanical equipment is up in this mezzanine, some electrical too, and it serves the clean room down below. So that's how low to floors you can get, on a low to low floor, you can get a clean room into a building by cutting the hole and making the whole volume larger with your service above. So we get into the planning, some lessons learned that we had is, we want to help the client understand the market and the difference between an incubator, an anchor, and a flex space, so that they understand what they're looking at and how to treat that in their lease structure deals. You want to have a clear basis of design that is developed early in the project based on everybody's understanding, and then you frequently visit that or revisit that And not just the MEP side, the architecture, the lab planning, everybody has to revisit it because it will evolve, it will change. And it's just an important document to identify that it is changing, which change is okay, but how is it changing and why is it changing? So as long as it's documented and it's understood and everybody's on the same page, that's what we're talking about, so that you're all going in the same direction. So that's in establishing the criteria and then creating the basis of design. Verify how much of it needs to be flexible, because I may be doing a flex space where I'm putting in one set of labs day one, but the infrastructure size for day two, and I got another set coming in, or how much of it is going to be modular so that we can actually, drop in pre-manufactured clean rooms, stuff like that. And what's our redundancy requirement? What are they going to be doing in the lab? So I have to have redundant air conditioning and power and exhaust. Is it that critical? But flexibility is one of the key things to do here and understand. And understand the structure of the building. Like Steve said, what can I physically put on the floor? What can this building hold? What can I put on the roof? What dunnage am I going to need? So all of that goes in up front. But when we get into like the implementation of it, and one of the key things we always recommend is include trade subcontractors and CMs in the early stages so that you're getting more accurate pricing, because as you know now, wood and steel are going through the roof and they have their finger on the pulse of the materials. So you want to get them involved for that. They can look at constructability issues, how we route different things, how we locate, where we locate different things, how we're going to get it up on the roof. All of these things are key that they can actually come in and provide clean input. Like you may think, wow, I could just take a regular crane and lift this unit up on the roof. Well, it turns out the crane sits on the road as a subway. Now there's certain structural implications to the subway before I can put that crane out there. So there's things like that that have to be vetted thoroughly. Okay. I think there was a question that popped up.
Yeah, there was a question. What kind of certificate is needed to be recognized as a lab space after an office space, like lab space conversion?
Well, so that's one thing that you need to go through with the architect to identify what is the code going to require. I'm converting a portion or a large portion of this building to a different use. Is my use requirement going to change with the code?
And one thing to tag on that too, that I'm wondering if that has to do with commissioning. As I say, you're definitely with a laboratory space that tends to get commissioned by a third party, just to verify that the systems are performing as intended. But of course, commissioning does occur even on office buildings, especially anything that's lead based. But then also circling back to Chuck's point, I mean, there's not a specific certification that is applied, so to speak. Even if you look at I'll say the building code side of it, whether it's an office building or a lab, they tend to be rated as Class B business oriented type structures. So they're very similar in the way they're made from the I'll say the shell side of it. It's really the MEP stuff tends to be different, but it doesn't require a special certification. But as Chuck mentioned, definitely need to meet code requirements regarding some of these specialized systems. And then, of course, as I mentioned, the commissioning is a one way that most lab, if not all lab type designs tend to be, or construction installations tend to be commissioned.
So one other thing though, specialty rooms, like a clean room. Clean room would be certified if you want a certified clean room. So whether it's class 10, old days, class 10,000, 100,000, those would need to be certified in order to have a true clean room.
Right. And then again, to add to that, some of that certification occurs through the testing and balancing. Your testing and balancing contractor would also certify. If the testing and balancing contractor is not qualified, there are other firms that are similar to that testing and balancing agency that will certify. Same thing happens actually with their fume hoods. They do need to be certified for airflow and velocities, and that tends also to be done along with the testing and balancing. But again, sometimes it may be done by a special agency contracted to do the work, but they're essentially a testing and balancing type firm.
Next slide. Well, we're done. Any other questions? Do we have contacts for consultants that could serve on smaller scale medical office lab conversion projects? That would be us. Okay,
All right, well, thanks, everyone.
thanks everyone. Have a great weekend.